Throughout the semester, you've no doubt noticed that there are functions that we would write using a for loop in Java and similar languages, but in Shplait, we just write a recursive function. We're now in a position to explain why Shplait doesn't need a special for form for loops. Let's simplify things a little bit by just considering infinite loops. So in Java or C++ or similar languages, while one with an empty body will just run forever. It won't run out of space, it'll just keep running until you stop the program. That's in contrast to writing a function that calls itself and then calling that function. The function will keep calling itself, but eventually it'll run out of space. That's because these are different kinds of computations in those languages. But what about in Mo? So here I've written a function f that receives itself as an argument, so it ends up calling itself forever, similar like to the f function that we had in the previous slide. But what will happen in Mo? Will this keep running forever, or will it eventually run out of some space and stop running? We can answer this question by seeing what it should do in terms of the substitution definition of Mo. So if we have let f be this function and ff, the way that let works with substitution is we just take this function and drop it in place of both of those f's. So we have the function applied to itself. Now this is a funny looking function call, but we've got a function expression and an argument. So we can perform this function call by taking the argument, substituting for f everywhere in the body, which is ff, so of course we get right back to where we were. So if you view it from the perspective of substitution, and you just keep writing each new step on, say, a piece of paper, it always will fit on your piece of paper. You will never run out of space. And it turns out that our implementation of Mo in Shplait also has that property, including when we're representing continuations ourselves. To see that, let's step through the interpretation of this expression. We have a function applied to itself in the empty environment and the done continuation. Now I should warn you that this interpretation is going to take several steps. I'll try to just hit the high points and go through it quickly. When we interpret a function call like this, an appy, then we start interpreting the function position, and we remember to interpret the argument expression later. Right? So we have an apparg_k remembering the argument expression. Meanwhile, we start interpreting the fun expression. When we interpret a fun expression, we get a closure back right away. Closure remembers the argument name f, it remembers the function body, f applied to f, and the current environment, empty environment, and we continue with the current continuation using that closure. When we continue with apparg_k, the meaning of apparg_k is start interpreting this argument expression, and remember in the future to actually perform the application. And to do that, we need to remember the value that was passed to closure, to continue. So we remember this closure in the do app_k, along with the rest of the continuation, which is just done_k. Now, once again, we are interpreting a function expression, so we get a closure expression right away, and continue with the current continuation. When you continue with do app_k, that means you have a value for the argument, and you have a value for the function, and so you want to call this function on that argument. That means we're interpreting this function's body in an environment that binds f, the argument, to the value that we are supplied, which is this closure. So we bind f to that closure, starting with the empty environment from the closure that we're calling. So now we are interpreting f applied to f in this extended environment. This environment is big and important enough that I'm going to abbreviate it with E1. And so E1 is that environment. We are just going to interpret f applied to f in that environment. Right? Now this is a key step in our interpreter. Remember this shape, because we're interpreting f applied to f with this environment, and we don't have to do anything else after that. To interpret a function call like this, we start by interpreting the function expression, that's just f, and we remember the argument to interpret later. When we interpret f in the environment E1, we just look up f and we find that closure that we had there. So now we are continuing with that closure and the current continuation, which is an apparg_k continuation. Apparg_k means start evaluating this argument expression in its environment. Remember the function because we need to eventually apply that function. So remember do app_k says apply this function eventually. Now we are once again in the position of interpreting a function, an identifier in an environment. So we just look up f in E1, it's still that same closure. And we continue with the do app_k. Do app_k means we now have the actual function we want to call and the argument to that function. Start evaluating the function body, extending the environment, and so on. And it turns out we end up with that same extended environment that we had before, with the same expression to interpret that we had before, and the same done continuation. So our interpreter gets back to the same state that it was before, which means our continuation here does not keep growing. That continuation corresponds to the stack in a language like Java or C, and so you see a difference here with Mo, that we can keep calling, a function can keep calling itself without growing the continuation, without running out of memory there.